Okay, here's a picture of Aristotle, the ancient scientist, and here's something that he believed. He believed that all science could be achieved primarily through reason alone. Just thinking about something long enough could give you the right answer in terms of science. So no experiment need be performed, and no peer review of your material need be sought, because if you thought about it long enough, then you should come up with the right answer. Well, this kind of thinking, this kind of approach to science is probably one reason why science didn't really progress much beyond this kind of point, because if you believe that only thinking can do it, then everybody thinks they have the right answer, and no progress can really be made. So it's really when the scientific method introduced by Gallio kind of gave a series of rules that could be applied to really discern whether or not you have a scientific fact or not. So the Aristotelian idea of science was eventually rejected, and hence progress could be made. One thing that Aristotle believed was that the earth was not moving because he could not observe parallax, and this shows you how bright he was. I mean, he was very brilliant, because to even come up with the idea that you could test for the earth's motion by parallax is something phenomenal. But as we know, the parallax that needs to be observed is too small to be discerned by just human recognition. That you would need special instruments to measure stellar parallax. So he's brilliant, but yet his conclusion was incorrect. Along came Ptolemy, who had this idea of the solar system. He thought that the Earth was the center of the solar system, and that the celestial sphere and the whole sky went around the Earth. And as you observed the skies over the course of months, you would notice that there were bright objects that moved against that sky over the course of months. And these bright objects were called planets. And the planets moved along particular paths called deferents. And Ptolemy proposed that these paths of the planets, deferents, were independent paths along this celestial sphere. One interesting thing, though, is that if you observe the path of the planets, you would note that they were close to the line of the sun's path on the celestial sphere, the ecliptic. And if you observed it over the course of months, there would be a point where you would see that the motion of the planets would kind of backtrack. They kind of do a loop-to-loop over the celestial sphere over the time period of several months. And in particular, here's a look at Mars. If it were headed in one direction in the course of several months, then it would backtrack, kind of do a loop-to-loop, and then continue on its way after that. So these wanderers, these planets, would do this loop-to-loop in the sky. For Mars, this would occur near opposition. Opposition is when the Earth is between Mars and the Sun, and hence Mars is basically at its closest approach to the Earth. And for the inferior planets, it would occur near inferior conjunction, which is basically the same idea, that the Earth would be Venus. Let's say if we say this is for Venus, Venus would be in between the Earth and the Sun, and hence it would be at its closest approach to the Earth when the Earth, Venus, and the Sun would line up. So we would observe this loop-to-loop behavior when the planets and the sun were all lined up. Well, Ptolemy would explain this behavior by saying that the planets are following these deferents, these paths, but when they reach this point where they would be in between the Earth and the Sun, then they would do an extra loop called an epicycle, and hence this would explain this loop-back behavior that we observe in the sky. The problem was that if you assume that the Earth is the center of the solar system, and you have the two inferior planets and the Sun actually being the third object going around the Earth in this scenario, that if you accurately pinpointed the positions of the planets over time, if you had accurate data, and you used this Ptolemaic solar system, then you would need more than one epicycle to explain the positions of these objects. In fact, you would need many epicycles to explain the positions of these objects. You would need circles within circles. You need epicycles upon epicycles to explain the exact positions of Venus, Mercury, the Sun, Venus, Mercury, and the other planets, Saturn, Jupiter, and Mars, over time. And in fact, it become quite complicated, and really probably would need a computer to calculate the positions of the planets at any particular time. Well, along came Copernicus, Nicholas Copernicus, lived from 1473 to 1543, and he proposed the heliocentric model, a sun-centered solar system. With this proposal, Copernicus was able to explain this loop-back behavior of the planets. Now, he did not propose this sun-centered model of the solar system until the last year of his life, because he knew it would be unpopular, especially with the religious beliefs of the day, and hence he figured, you know, he was near the end of his life. What could they do to him then? So that was the time to propose a new idea of the solar system. But here's how this loop-back behavior works in the Copernican or sun-centered, helio meaning sun-centered solar system. If you have Mars, which is the outer planet, and you have Earth interior to Mars, Earth is traveling around the Sun faster than Mars is. Hence, Earth would see Mars against a different backdrop of stars at various times. If we look at position 1 here, Earth sees Mars and particular backdrop of stars over here, but Earth is traveling faster than Mars. So at any particular time, Mars starts to backtrack in relation to the much further out backdrop of stars, and hence Mars starts to appear, at least from our perspective, that it is going backwards in its regular path as Earth is approaching opposition. Finally, when Earth passes Mars and starts to continue on its way around the Sun, then at that point Mars continues on its apparent path across the celestial sphere against the motion, or the regular motion, from east to west of the celestial sphere on its nightly path. So the net effect is that Mars is moving this way, backtracks, and then continues moving this way. So just assuming this sun-centered or heliocentric model of the solar system allows to explain this loop-to-loop behavior of the planets. But Copernicus had one small problem. If he assumed circular orbits, which he did, that the planets were moving around in circles around the sun, then he still had to keep one small little epicycle for the planets, because using accurate data, he still couldn't explain all the loopback behavior. Along came Galileo. Galileo supported Copernicus's idea of a sun-centered solar system. He wasn't as smart about it because he published this idea long before his death, so it was reviewed over the course of his lifetime. But what he did was he supported this view through his observations of the recently invented telescope. The telescope was invented in the early 1600s, and Galileo immediately started using it and observing the sky. And here's what he saw. Galileo saw moons revolving around Jupiter. And in fact, the 4 largest moons of Jupiter, now called the Galilean moons, revolve around Jupiter over the course of days. So if you looked at Jupiter every day in successive days, you would see these 4 bright dots moving to different positions around Jupiter every single day. And hence this showed that some other heavenly body could be the center of motion, could be its own center of motion, and that things could go around it, and hence the Earth was not the center of all motion. Something else could have its own center of motion. Galileo also proposed that the Copernican system should be correct because of the way that he observed Venus. If you look at Venus, you can observe phases of Venus, but if you were under the geocentric or Earth-centered model, then you would guess that since Venus is between the Earth and the Sun and never gets beyond the Earth with respect to the Sun, that the best you could ever see of Venus in terms of lighting would be that it would be in its crescent phase. That since the Sun is illuminating Venus, there's just no way that you could get more than half of Venus ever lit from a geocentric perspective, because it's between the Earth and the Sun. But in the heliocentric model, at some point, Venus could be slightly behind the Sun from an Earth perspective, hence be more than half illuminated, and reach a gibbous phase. And in fact, this is what is actually observed for the phases of Venus. Hence, this is great support for the heliocentric model, and pretty much disproves the Ptolemaic or geocentric model of the solar system. Here's a picture of Galileo trying to explain this to the Catholic Church at the time. It shows 2 little pictures on his diagram here. One is showing Jupiter, and I believe with his 4 moons, so he's trying to explain that these moons are going around Jupiter, and the top one is showing the different phases of Venus. Now Galileo was a very religious man. 2 of his daughters became nuns, and he was great friends with cardinals of the church. So he was a great believer in the Scripture. He did not see any problem with the fact that he was saying that there was a different model of the solar system than was being proposed by interpretation of the Bible. That was his problem, was that the Bible wasn't wrong. The word given by the Bible was not wrong. It was just that the interpretation of that word was wrong. he made the argument that nature in itself is also the Word of God, and that the Bible and nature were both expressions of the Word of God, and each in its own right was true. However, this caused such an uproar that he was forced to recant his explanation of the solar system, and otherwise he would have been tortured by the Inquisition, and he was simply put under house arrest for the last 9 years of his life. Yet he was proposed to have muttered under his breath, "Yet it moves," meaning that the Earth moves in its orbit around the Sun. So here's a summary of some of the results of Galileo's discoveries with the telescope. One was that he saw the 4 Galilean satellites of Jupiter, and this basically showed that not all objects revolved around the Earth, that something else could have objects revolving around it. He saw all the phases of Venus, which would be impossible under the geocentric or Ptolemaic Earth-centered system. He actually saw craters and mountains on the moons, which showed that the heavens were not perfect. This was also in contrast to the prevailing thought of the day. He saw the movement of sunspots, and he used this to measure the period of rotation of the Sun, which was about a month in duration. So this showed that the Sun could rotate, and if the Sun could rotate, maybe the Earth could rotate as well, and this would explain why we see the whole sky move over the course of one day, that the Earth was rotating. And he saw the stars of the Milky Way, which was evidence of the Milky Way's galaxy long before the thought of stars and the Sun being part of galaxies was proposed. Incidentally, one good argument against Galileo's idea of the Earth going around the Sun was the fact that if the Earth were going around the Sun, it'd be moving really fast. And as we know, with things that move really fast, that there would probably be real large winds, and you wouldn't be, things would just be flying all over the place because we'd be on the Earth as well, and nothing could be secured because things would be flying around. Because if we calculate, as the Earth is going around the Sun at its great distance, it would have to be moving at a great speed, and in fact the speed would be about 30,000 meters per second, which is 30 kilometers per second. Incredible speed. Life had to write sort of cryptically to answer these questions, and one way he answered this question was the fact that he told a story. He said that, say you're on a ship traveling through the sea, and you climb the masthead to the top of the crow's nest, and let's say you dropped a ball from the crow's nest and let it fall towards the bottom of the ship. Now the ship's traveling fast through the sea. Where would this ball land? Would it land directly below the crow's nest? Would it land behind the masthead, or would it land in forward of the masthead? Because the question is, if we're on a moving ship, does it fall behind, fall straight down, or fall ahead? And the answer would be, if you're on a moving ship, ship is moving ahead like this, and you drop a ball from, or drops anything from the top of that ship, when you drop it, it's already moving with the ship. So both of them are moving forward with the same speed, so when you drop it, it just falls with respect to the ship straight down. So if you were at the top of the masthead and you dropped a ball, it will fall to the bottom of the masthead just like it were at rest. In other words, and with respect to the ship itself, everything that's moving at that same speed is the same as if it were at rest with that frame of reference. And his point was that if we were on this moving Earth, everything on the Earth is moving at the same great speed, and so with respect to the Earth, it's the same as if we were at rest with respect to the Earth. So that's why we don't see things flying around and these great winds created by the Earth's movement through the solar system. Here's Tycho Brahe. He was the greatest astronomer of his day. He measured the exact positions of the planets every night for 20 years. And he didn't have a telescope. He used a sextant, astrolabe, to measure the positions of the planets. But his measurements were so accurate that these were the best measurements made of the positions of the planets for the next 300 years. So he was well known as the best astronomer of the day. You may notice, and it might be hard to see on this picture here, that there's something wrong with his nose, and in fact, Tycho Brahe had a fake nose. The reason he lost his nose was because he and another student in college had an argument over a math problem. They were in a math class, and Tycho Brahe said he was right, and the other guy said he was right, and they really couldn't prove to each other who was correct on the math problem. So they decided the only logical way to solve this problem was to have a duel. So they had a duel at dawn, and the other guy lopped off Tycho Brahe's nose, and so evidently he was right. So for the rest of his life, Tycho Brahe had to wear a fake nose. So he would have this nose, and he'd use this putty that of some origin that he would put on to hold his nose in place, and he had to do that for the rest of his life. So the picture kind of shows him with his fake nose. Another interesting feature of Tycho Brahe is he had a pet moose. And this moose would make itself at home. It would walk into his house and walk around and walk out at will. And unfortunately, the moose met its untimely demise one day when it walked into his house and made its way upstairs. And it found a vat of beer at the top of the stairs, and the moose drank from that vat of beer, and when it was done, he tried to make his way back down the stairs and wasn't too successful. So unfortunately, that was the demise of Tycho Brahe's pet moose. One other thing that Tycho Brahe found was he saw that Mars varied in brightness from time to time at near opposition, and he correctly surmised that maybe at these points Mars was closer to the Earth than at other times, and hence maybe the orbit of Mars was not circular, but maybe its orbit was instead elliptical, or just basically not circular. Tycho Brahe had an untimely demise as well, and that might be something you may wish to research on your own. But he died under peculiar circumstances, and a few years ago, about 5 years ago, his body was exhumed for the possibility that maybe he might have been poisoned. and so they examined his hair, and it did find that there was some lead or mercury poisoning in his hair. And the possibility is that maybe he poisoned himself, because maybe the putty that he used to keep his nose on had some lead in it, and he might have accidentally poisoned himself. In the last year of Tycho Brahe's life, he took on an apprentice, Johannes Kepler. Kepler was a mathematician. He wanted to look at Tycho Brahe's data so he could come up with some formulation of the motion of the planets. But Tycho Brahe was not willing to give up his data, so he said, "Data's mine, I can't have it." Well, within a year of taking on Johannes Kepler as apprentice, Tycho Brahe died. Some people have postulated that maybe Kepler poisoned Brahe, but that has not been proved. But finally Kepler got the data, and he studied the data for the next 16 years and came up with his 3 laws of planetary motion. Here's Kepler's first law. The orbits of planets are not circles, they are indeed ellipses. And if you know from a mathematical presentation of an ellipse, you have 2 focus points on an ellipse, and as you draw the ellipse, the distance is constant, the total distance is constant to both focal points. So you would draw kind of a scrunched down circle, which is what we call an ellipse. So in Kepler's first law, the sun is at one of these focal points, and the planet actually goes through this elliptical motion. So sometimes it's closer to the sun, and sometimes it's further away from the sun. For this ellipse, we define what we call the eccentricity as the ratio of the distance between the 2 focal points to the distance of the semi-major axis, the longest axis of the ellipse. And we can see if the ellipse is scrunched down like this, then in this particular case those distances are pretty close, and so this would be a ratio close to 1. So for a very flat ellipse, you get an eccentricity close to 1. But if the ellipse were a circle, in other words, if these 2 focal points were closer together, in fact right on each other, then you'd have 0 over this distance of the diameter of the circle, and hence for a circle the eccentricity is actually 0. Most of the planets have eccentricities close to 0, so even though they are going through elliptical motion around the sun, the ellipses are not scrunched that much. They're very close to being circular. Here's Kepler's second law. The planets sweep out equal areas in equal amounts of time. So if we chose the same amount of time, say 1 month, that the planet, if planet was going around an ellipse around the sun, that the planet will sweep out an equal area, an equal slice of pie in that same month. The point is that when it's closer to the sun, it's moving faster, so that slice of pie is wider, and when it's further from the sun, it's moving slower, so that slice of pie is narrower, but still the areas are equal. Incidentally, the Earth is closest to the sun in January at perihelion. Peri meaning closest, helion meaning sun. Closest point to the sun is January 4th for the Earth, and the aphelion, the furthest point from the sun, is July 5th for the Earth. So we are actually closer to the sun in January than we are in July, and that's further proof that the seasons are due to the tilt of the Earth and not necessarily due to the location of the Earth with respect to the sun. Here's Kepler's third law. It's called the Harmonic Law. The square of the planet's orbital period, measured in years, is equal to the cube of its semi-major axis, measured in astronomical units. You could write it like this. The time it takes for a planet to go around the sun, that time squared, is equal to some constant times its distance from the sun cubed. How he came up with this, I don't know. It's an empirical law. It's just a law based on data, but he had 16 years, so he just poured over this data for 16 years and came up with these relationships of the planets, and they were indeed correct. So this is an amazing law. Here's some data on our planets, except it includes Pluto, which is currently not a planet. It's just a dwarf planet. But we can see that this ratio, measured in years per astronomical units, is very close to 1 for all of the planets. And we also have the eccentricity of the planets on this table. We see most of them are very close to 0, except for Mercury and Pluto. Here's an example of the harmonic law. Let's calculate the period of a planet whose orbit has a semi-major axis of 1.52 astronomical units. Well, the period squared shall equal, in this case, 1 times the distance of the planet from the sun cubed. So we'll say the period squared equals 1 times 1.52 cubed. So that's the period squared is 3.51. Take the square root of that. So the period for this planet should be 1.87 Earth years. And in fact, this planet we're talking about is Mars. So Mars is 1.5 times the Earth distance from the sun. In other words, it's 50% further away from the sun than we are. And because of that, it takes 1.87 Earth years for Mars to go around the sun. This could be used in reverse. If you measure the time it took Mars to go around the sun, then you could figure out how far it was away from the sun. Along came Isaac Newton, sort of the father of modern physics. He was born in 1642, which happened to be the year that Gallio died. So sort of the torch, or maybe even the soul of science, was passed between Galileo and Isaac Newton. Newton is famous for coming up with the first formula or theory of gravity, and it's been proposed that he first thought of this accidentally when an apple fell from a tree and hit him in the head. Here's some other things that Newton came up with. He devised the basic concepts of motion, which we're going to talk about. He invented calculus. I usually say that he invented calculus just so he could do more physics. That's the main reason to do math, at least in my opinion, is so that you can do physics and think about nice things like astronomy. He explained the gravitational effects of the moon and the earth. He devised the universal law of gravitation, which we're going to talk about. He invented the Newtonian or reflecting telescope, which is actually better designed than the refracting telescope that is used most often. The reflecting telescope has less amount of things to go wrong, so it's an intelligent design to observe the heavens. He showed the spectral nature of white light. He observed that when white light passed through glass, sometimes it would break up into these other colors, and Newton was brilliant enough to realize that those other colors all comprised white light. He published How could Newton do all this stuff? I mean, that's an incredible feat, especially to do all that by himself. And it's really against the scientific method, because scientific method requires you to have a peer review and to have everybody bounce their ideas off you, so you can really refine your ideas and get it right. But he got it right the first time through, and so it required a lot of work, a lot of time, and part of the reason he had that time is he had a pretty good job. He worked for the mint, and so if he ever needed some extra dollars, he could just print out some more extra dollars with his face on it. So he could just spend his time working on physics. Here's Newton's first law. An object at rest remains at rest, or an object in motion continues at constant speed in a straight line unless it experiences a net force. The first part of this law kind of makes sense. And you say an object at rest remains at rest. Yeah, I mean, if there's no net force on it, there's no impetus to make it move, yes, it should remain at rest. But the second part of the law kind of defies normal intuition. An object in motion continues at constant speed in a straight line forever and ever and ever unless it experiences a net force. So it's saying the natural state of things is to move at constant speed in a straight line forever unless you experience a net force. Well, we know in every day that you could push something, slide it along the ground, and it comes to rest. So it doesn't continue at constant speed in a straight line forever and ever and ever. What gives? Well, you probably know the answer. If we push something and let it slide and let it come to rest, it's experiencing a net force. That net force would be friction. So if you were to do the same sort of scenario out in space, if you gave something a push out in space, it will go forever and ever in a straight line at constant speed, forever and ever, unless it experiences a net force, unless maybe the gravity of a planet will suddenly pull it into it, and then that will change it off course. So if you're out in space and you give somebody a push, they will move at constant speed in a straight line forever and ever. Here's Newton's second law. If there is a net force, it is proportional to the mass of the object and the acceleration of the object. It's actually the most famous law in physics, F equals ma. Basically, this says that if you give something a push, a force, that force will be proportional to its mass times its acceleration. So the more massive it is, the less it's going to be accelerated by your force. And the less massive it is, the greater it's going to be accelerated by your force. So that's why when you push the Earth, if you were to give the Earth a push, it's not going to do very much, because the Earth is so massive, and hence the acceleration that you impart on the Earth would be extremely small. Here's Newton's third law. For every action, there's an equal and opposite reaction. For instance, this ram, we're butting heads with this ram, and if there was one force in one direction, say by ram number 2 on ram number 1, there will be an equal and opposite force on the other ram. In other words, as they collide, they both will feel the same magnitude of force, but in opposite directions. And this law is true whether or not you had two physical pushing objects like this. Let's say you were thinking about the universal field theory, and you just can't get it right, and so you butt your head against the wall, like Einstein might have done. And so while you impart that force on the wall will impart that same force back on you. So there's no way around it. Any force you impart on something is going to be imparted back on you. So forces always occur in pairs. A single isolated force does not exist. And philosophically, this is kind of interesting if you look at the universe. Anytime you have an extra force in the universe, then there's a equal and opposite force as well. In other words, whatever force exists in the universe now is constant. Anytime you add a new force, there'll be a negative force associated with it, so the net force in the universe will not be changed. You exert your weight against the Earth exerts a force on you, pulling it towards the center of the Earth, and at the same time, you exert a force on the Earth towards you. The reason why the Earth is not pulled off its course around the Sun is because it's so massive, and your force on the Earth then exerts very little acceleration on the Earth. Here's a little cartoon that I like. Here's Newton trying to think of new ideas with his scientific friends, and they're all sitting around the trees, and Newton's asked them, have you thought of anything yet? And one of his friends goes, nah, nothing yet. How about you, Newton? And Newton's working away, but he's about to discover in a big way the theory of gravity, because the apple's about to fall on his head. Here's Newton's law of gravity. And you don't have to know this law of gravity mathematically, you just have to know its implications. The force of gravity is equal to some constant, it's a universal constant called the gravitational constant, times the mass of one body times the mass of the other body over the distance between them squared. So the force is proportional to the mass of each body and inversely proportional to the distance between them squared. So if a satellite were to increase its orbital radius, say, by 4 times, then the force of gravity between the Earth and that satellite would decrease by 1 over 4 squared, or 16 times, and be 1/16 as much. So it drops off fairly rapidly. Let's try this force out. What does the force of attraction say between Ben and Jen, Ben being 75 kilograms and Jen being 55 kilograms, if they are 1 meter apart? Oh, okay, let's replace Jen by Jen so that we can update our notes here. So Ben and Jen are 1 meter apart. What is the force of attraction between them? Well, it's that gravitational constant, which I didn't tell you what that was, but it is 6.67 times 10 to the minus 11. We have the mass of Ben, 75 kilograms, the mass of Jen, 55 kilograms, and they're 1 meter apart. So this force is 2.75 times 10 to the minus 7 newtons. Not enough to make them spontaneously collide, because there could be molecules of air which would provide definitely enough friction to not make this happen. And in fact, we could even think about the force of attraction, say, between you and the Andromeda galaxy. The Andromeda galaxy is incredibly massive, but it is so far away, 2.9 million light years, in fact, that that r squared term makes it insignificant as far as being a force on you. It really would be so incredibly small that you really don't feel that force. But that's because it's so far away. This force of gravity is responsible for the motion of things that we see happen near the surface of the Earth. In particular, parabolic motion if you were to throw something, you would see it go through a parabola, a curve, and that's because it's following the pull of gravity is pulling it down towards the Earth. Well, here's a thought. If you were to travel to the highest mountain on Earth, and let's say, actually maybe not Earth, maybe a planet that doesn't have any atmosphere, so there's no air friction, and you were to throw a ball as hard as you could horizontally, well, maybe not as hard as you could to begin with. If you threw it pretty hard, it would follow a parabolic path and be pulled towards that planet along this path. Let's say you threw it even harder, it would follow a more or less parabolic path, but it might go a little bit further before you hit the planet. So you threw it even harder, and it would follow this path, being pulled down towards the planet, but maybe eventually hit the planet here at point G. So you give it a really good throw. So it's being pulled down towards the planet by gravity, but as it's falling towards the planet, it's also moving forward, and it continues to fall towards the planet and moving forward along the curvature of the planet, and in fact it goes all the way around the planet back to where you are and you catch the ball. In other words, we can think of satellite motion the same as if you were moving forward in a horizontal direction as fast as you could, but at the same time falling towards the planet, but you move forward so fast that that fall towards the planet never actually pulls you closer to the planet. It just makes you fall around the planet in a satellite motion. And this really is what happens with satellites. If you think about the shuttle and weightlessness, if you look at the astronauts, they always look like they're weightless, like there's no gravity on them, but there in fact is gravity on them. They are actually bound to the Earth by the force of gravity, and it's not that much less than the gravity we feel at the surface of the Earth. The reason why they look weightless is because they are falling the whole time. They're moving in a forward direction so fast, but they're falling at the same time that they are indeed weightless. The same kind of effect that you have when you get into one of these rides at, say, Six Flags. If you have a demon drop ride where you get into a elevator type object and you fall, and for that time that you're falling, you feel like you're weightless, like there is no gravity on you. And in fact, that's the effect of just falling. But indeed, you are being pulled towards the Earth by gravity. So an object going around the sun, or a planet going around the sun, is actually being held in its orbit by gravity. And that gravity is just enough to keep it in its orbit, not any more or not any less, because it's kind of settled into that situation where it's not being pulled towards the sun, it's just being held in a elliptical orbit around the sun. Now, if you had two objects doing this, they would actually revolve around their own common center of mass in elliptical orbits, somewhat in this figure as you see here. But the sun is much more massive than the planets. So if you had a larger mass, like the sun, then the sun would kind of go through a wobble of an elliptical orbit, and the other object would wobble about its common center of mass with the sun. The net effect is that the sun just kind of wobbles back and forth. The planets go through an elliptical orbit with the sun at one focus, but really they're both orbiting their own common center of mass, and the net effect is the elliptical orbit that Kepler proposed for the orbits of the planets. And that's why the orbits of the planets are not circles, they're ellipses, because the planets are not necessarily going around the sun, they're going around the common center of mass between the sun and the planet. But that common center of mass is actually not far from the sun. It's actually located within the sun, a little bit off the center of the sun as the sun just kind of wobbles around. This concludes lecture number 2 for chapter 1, and hopefully has given you enough information to answer most of the questions in the binder.